Section 5.2 is probability distributions. This is where we create our probability distribution. It gives the probability for each value of a variable that is determined by chance. This variable is called our random variable. We're also going to look at what we consider to be usual and unusual values. So we're going to start though with a random variable. When we use an uppercase variable to describe something, that's the random variable. Any particular outcome then would be a lowercase variable. So for instance, if I let X represent the number of girls born in a family, this lowercase x would then represent either 0, 1, 2, 3, which would be the number of children. But the random variable is what the numbers for the little variable represent. It has a single numerical value that's determined by chance for each outcome of a procedure. The probability distribution is a description that gives the probability for each value of the random variable, often expressed in the format of a graph, table, or formula. We're going to focus on tables today. We have discussed discrete and continuous random variables. For instance, the length of your foot would be a discrete or continuous random variable. The length of your foot. Continuous, your shoe size would be discrete. Probability distribution requirements. In order to have a valid probability distribution, the sum of all the probabilities has got to be equal to 1. This correlates to the fact that when we had our Venn diagrams, we said that the rectangle represented our sample space. We said the probability of our sample space was equal to 1 because the sum of all possible outcomes has to be equal to 1. Also, probabilities have values only between 0 and 1. So you can't have negative probabilities. You can't have a probability greater than 1. All right, let's look at an example of how we can use this information then to create a probability distribution. It says accidental death or disability insurance. Suppose actuarial results indicate any individual has a 1 out of 1,000 chance of dying in an accident and a 2 out of 1,000 chance of becoming disabled. The insurance company pays $10,000 to the beneficiary in the case of death and $5,000 to the policyholder if they become disabled. What we want to do is create a probability model here and then answer the question, how much should you expect to pay for this policy? So we're going to start by listing the possible outcomes for an individual who purchases this policy, and that will help us then determine what our random variable x is going to be. Remember, x has to be a numerical value for your random variable, and then once we know x, we can determine p of x, the probability of that happening. So if we're talking about an insurance policy, there are two outcomes. First outcome, you could be fine, nothing happens to you. Or you could just get hurt in the accident. We'll call it 5,000 if you're disabled, and dead. Those are our three outcomes here that could happen if you purchase this insurance policy. If you're dead, you get nothing, but your family gets how much? They get $10,000. If you're hurt, you get how much? 5,000. And if you're fine, you get how much? Nothing. Remember, this is our random variable, x. Your random variable has to be a numerical value. So these are the numerical values. You don't have to include this column for the outcome, but I think it kind of helps you see what numbers to put where. We told that there's a 1 out of 1,000 chance of dying in an accident. So the probability of dying is 1 out of 1,000. The probability of being disabled is 2 out of 1,000. What's the probability that nothing happens to you at all? 997 out of 1,000. Remember, all of the probabilities for the model have to add up to 1. That came from up here. The sum of all the probabilities has to be 1. So if we add up all of the possible probabilities here, we've taken everything into consideration. So this is our probability model. The second question here was, how much should you expect to pay for this policy? Well, I don't know. It depends on how much I expect to earn. There's 997 out of 1,000 chance that I get nothing. If that happens, my net gain is nothing. What I'm looking at here is x times p of x. there's a 2 out of 1,000 chance that I'll get $5,000. So 5,000 times 2 over 1,000 is how much? 5 times 2 is 10. And then 10,000, I get 10,000 if I'm dead or my family does. So 1 over 1,000 times 10,000 is 10. If we add up the random variable times the probability that that's going to happen, we see here what we call the expected value. And that's going to be the sum of what the random variable is times the probability that that particular random variable occurs. And in this case, it's 20. So we should expect to pay at least $20 per unit or per $1,000 of coverage here. If the insurance company sells these policies for less than $20 a unit, then they're going to take a loss because they're playing the odds and averages. So they need to sell this policy for at least $20 if they just want to break even. Odds are they want to make a profit though. So what we just saw, this 20 is actually the expected value, and how we come up with this is we take the sum of x, our random variable, times p of x, the probability of that random variable. So this is a formula. You might want to add this to your formula sheet, your list of formulas that you're accumulating. Now let's see if we kind of get an idea of what's going on. It says one of the authors of this book took his minivan for repair recently because the air conditioner was cutting out intermittently. The mechanic identified the problem as dirt in a control unit. He said in about 75% of such cases, drawing down and then recharging the coolant a couple of times cleans up the problem and costs only $60. However, if that fails, then the control unit must be replaced at an additional cost of $100 for parts and $40 for labor. Part A to this question says define the random variable and construct a probability model. What is our random variable going to be here for this scenario? Your random variable x is going to represent the cost of repair. So when we construct our probability model here, we have our random variable x, and then we have the probability of that particular event occurring, and that's p of x. Just because I find it helpful, let's list what our outcomes are. What are the choices here for x, or for a random variable? Recharge, we'll call it. Drawing down and recharging, and then the other one is replace. If the recharge works, how much is it going to cost? $60. If they have to replace the unit, an additional $140. So that would be $200. Because they're going to try the recharge first, and if it doesn't work, they're still going to charge you for doing that procedure on your van. Alright, the probability that the recharge works is 0.75. And then if they have to replace it, what's the probability that that happens? We weren't told that probability, but we can figure it out, can't we? What do all the probabilities have to add up to? 1. So we've got 75. This is going to be 0.25. So this answers part A to this question. Define the random variable and construct the probability model. Part B says what is the expected value? Well, in order to answer part B, I need that column x times p of x. And this is going to answer part B. So 0.75 times 60 is, and 0.25 times 200 is. So what is the expected value? $95. That's the expected value. What does that expected value mean in the context of this problem? Is anybody really going to pay $95 to have their van fixed? No, they're either going to pay $60 or $200. But the expected value is what the mechanic or the shop can expect to earn on average over time. If they know that during the course of a month they have X number of vehicles come in with this particular problem, and they were trying to anticipate a budget or a revenue, then they could take that number of problems or number of vehicles and multiply it by $95 to get the expected value. On average, this is what you would expect the repair to cost. Now there's some more formulas here that you want to add to your formula sheet. You guys are accumulating a formula sheet that you can use for your exam. I'm not going to make you memorize all these formulas. The expected value, another word for the expected value, is the mean. It's an average. The variance, remember, is the square of our standard deviation. The variance is a measure of spread. The mean and the expected value is a measure of the center of the distribution. Variance measures spread. Take the square root of the variance and we have the standard deviation. Now here's a shortcut for the variance, but I'm going to show you guys how to use your calculator and lists in order to find the variance. So it doesn't really matter which one of these you use. Is everybody done writing down the formulas? They will be on the lecture notes that I will post. All right, let's look at another problem. Number 19. It says a consumer organization inspecting new cars found that many had appearance defects, dents, scratches, paint chips, etc. While none had more than 3 of these defects, 7% of the cars had 3 defects, 11% had 2, and 21% had 1 defect. Find the expected number of appearance defects in a new car and the standard deviation. In order to do this problem, the first thing you need to do is create this probability table. X represents the number of defects that you have in a car. Remember, your random variable has to be a numeric value. In this case, it's a discrete numeric value. So how many defects, what values are we going to put down for X? 0, 1, 2, and 3. Give me some probabilities. 7% of the cars had 3 defects. 11% of the cars had 2 defects. And 21% of the cars had 1 defect. We weren't told how many of the cars had no defects. Is that a problem? No, because we can figure it out, can't we? How am I going to figure it out? Add these 3 numbers up and subtract it from 1. And when we do that, what do we get? 0.61? Thank you. Now, the first thing that we're asked to find here is the expected value, the expected number of defects. In order to do that, we need to find X times P of X, and then we add all that up. We're going to do this on our calculator. So we go to our Stat button and edit. We're going to edit a list of values. In list 1, we're going to plug in X. So there's 0, 1, 2, and 3. Move over to list 2. We have 0.61, 0.21, 0.11, and 0.07. List 3 I can find by using the information from list 1 and list 2. So I'm going to highlight the name of the list. Notice I move my cursor up to the name of the list. And I type in second 1 for list 1 times second 2 for list 2. And notice it puts this right here on the formula for list 3. Hit enter and it actually populates the list with the following probabilities. So we don't have to sit there and crunch it out by hand. So this is 0, 0.21, 0.22, and 0.21. So the expected value is going to be the sum of everything in list 3. Well, the way we're going to do that, rather than, I told you I don't feel like doing arithmetic today, so we're going to quit the stat program, hit second list, which is second stat, and now I want this to do some math for me. I want it to find the sum, which is number 5, so I highlight math and hit 5, and we want to find the sum of list 3, so I hit second 3 to get list 3 in my calculator, and it's 0.64. So that finds the mean, the measure of the center of this distribution. Now I need to find the standard deviation, but I'm going to find the standard deviation by way of the variance. So I'm going up to my variance formula, and it says the variance is the difference between your data value and the mean squared times the probability of those data values. So this is the formula that I'm going to use right here. It doesn't matter which one of these formulas you use, it's just that this is the one that I've always used. So that's what I'm going to do. But in order to use it, I need to know what the mean was, and that was 0.64. So I go back into my stat program, and I'm going to edit, and I'm going to create a list 4. So I move my cursor up to list 4. Now list 4 is going to be X minus the mean, which is 0.64 squared, times P of X. So we go to list 1 was X. We use list 1. Oops, this needs to be in parentheses. List 1 minus the mean, which is 0.64 squared, times list 2, because list 2 is P of X. We hit enter, and it populates that list. Now, if we find the sum of this list, we've found our variance. So our variance is going to be the sum of X minus 0.64 squared times P of X. That's just the sum of list 4, so we're going to go back to the home screen, And we could hit second enter to bring back the sum and just move our cursor over and type over second 4 and get list 4 instead of list 3. Or you can actually go through the list math and hit second list math, number 5 is sum, and then tell your calculator there to use list 4. Either way, you get 0.8704. Now the standard deviation is this symbol, and it's just the square root of the variance. So for this problem, it's going to be the square root of 0.8704. And when we do that on our calculator, second square root, second answer, we get 0.9329. Let's see, let's round this to 3 decimal places. That's 0.933. So what we're looking at here is x is list 1, p of x is list 2, and then for list 3, we do list 1 times list 2. For list 4, we do open parentheses list 1 minus 0.64 squared times list 2. So that way you have the list. If it's bolded, you just put the list. The light red is where you actually had to highlight the name of the formula. These right here, you have to put the cursor on list name. So here's step by step what you need to do in order to get the mean and the standard deviation from the list. And remember, means and standard deviations give us the measure of the center and the measure of a spread of a distribution. And if your distribution is normally distributed, we can then find all sorts of things, knowing the mean and the standard deviation. Alright, identifying unusual results and the range rule of thumb. According to the range rule of thumb, most values should lie within 2 standard deviations of the mean. We can therefore identify unusual values by determining if they lie outside these limits. Do you guys remember our normal distribution that had this shape? It was symmetric and bell shaped. We're getting close to coming back to this shape a lot. We said that if the mean, if we know the mean, and remember for what we just did, the mean was the expected value, the sum of x times p of x. The mean lies dead set in the center. If we go out 1 standard deviation, what percentage of our data lies within 1 standard deviation of the mean? 68. If we go out 2 standard deviations, there's the mean minus 2 standard deviations and the mean plus 2 standard deviations. What percentage of our data lies within 2 standard deviations of the mean? 95. And then if we go out 3 standard deviations, we're at the mean minus 3 standard deviations and the mean plus 3 standard deviations. That ends up being 99.7. But all it takes to be considered unusual is for this to go out 2 standard deviations from the mean. So if anything's more than 2 standard deviations from the mean, we would consider that to be unusual. So back right here, when we looked at the dings on the car, we had a mean of 0.64 and a standard deviation of 0.93. Clearly this data is not normally distributed, because if we go out 2 standard deviations from the mean, we have negative dings, and that doesn't make sense. There's the mean, there's the standard deviation. Remember, this graph and these percents only work for normally distributed data. Now, we can identify unusual results based on probabilities as well, not just at the number of standard deviations above or below average. We say that if the probability of an event happening is extremely low, then we're going to call that an unusual result. For example, if the probability of an event happening typically is less than 0.05, we're going to call that event unusual. For example, getting 992 heads out of 1,000 coin tosses, that's unusual. The probability of that happening is extremely small, so we would conclude then that the assumption is probably not correct. We say that a probability is unusually high if X successes among n trials. If the probability of getting that is less than or equal to 0.05, it's unusually low if the probability of getting X or fewer successes is less than 0.05. So that's our cutoff here. We're going to stop here for today.